What we're going to talk about today is actually the Bellman equation, which is an important concept and component in reinforcement learning. The Bellman equation itself is nothing but a recursive equation that is representing the value of the current state as an expectation of the reward and the value of the successor state. So we have a current state, which we call ST. So the big ST means it's a random variable. And we set that to, some state S. So, we are in some state S. The value of this state, which is kind of the reward you will get, in the future for this specific state, is nothing but the expectation of the immediate reward you would get plus the value of the successor state. Now, I just note that I say here expectation. And the reason why I use expectation is because this is just like summation over probability distributions of some random variable. So if you would expand an expectation in terms of the probability distributions, right? So if you have expectation under some distribution P of some random variable X, then you expand that, you will get the summation of P of X times X. That will be your equation. And this is exactly what you see here, right? So this is nothing but the expectation over the policy and also like the MDP itself or the successor state. We're going to achieve this proof in 3 main steps. And the first step, as always, in any mathematical derivation, will correspond to defining our problem in a lot of details. So in order to define the value function, we are going to define a random variable, which we're going to call GT. And that random variable simply collects the rewards you would get from time t plus 1 onwards if you were at some state big ST, right? So from that state ST, you start executing your policy, transitioning to new states, executing your policy again, transitioning to new states, and so on. And now we define this GT as simply the reward or the sum of the rewards that you would actually be getting by executing that policy onwards. Please notice here that there is a gamma. That gamma is just a discount factor, so it's going to be less than 1 value. And the reason we have this gamma, there are different interpretations. Some people talk about how much you want to look ahead into the future. From a mathematical perspective, maybe pure mathematical perspective, gamma is introduced so that we avoid divergence of an infinite series. Because as you see here, gamma is less than 1, so gamma squared will be something smaller, and then gamma cube even more smaller, and so on. So therefore, this won't really diverge. Now, given this GT, the value of the state is simply the expectation of this GT variable or random variable, conditioned that we started at some state ST. So given that we started at this state ST, and we followed the policy pi, then the value of the state ST equals S is nothing but the expectation you would get of that random variable. And now, of course, we defined that random variable in this way, RT plus 1, gamma RT plus 2, gamma squared RT plus 3. So I could just simply replace it in this equation instead of GT and write it in the following form. So now I could write V pi of ST equals S is nothing but the expectation of RT plus 1 plus gamma RT plus 2 plus gamma RT plus gamma squared RT plus 3, and so on. Now, let's have a roadmap in mind, right? So our goal is to really write this value ST, right, as some, let's say, complicated function of the value of ST plus 1. And we defined the value of the state ST as the expectation of GT given ST equals S, right? So the value of ST plus 1 is nothing but the expectation of GT plus 1, right, given ST plus 1 is equal to S. So now we need to start here and arrive to a place where we can actually write this equation such that it has GT plus 1 inside it. Because if we have that, then we're getting closer to the Bellman equation, because then we remain to introduce the expectation over ST plus 1 somehow, right? Or condition, sorry, on ST plus 1. So how are we going to do that? Well, this is really not that complicated. All you need to do is we're going to leave RT plus 1 as is, so we're not going to change that, right? So it's the same here and here. But what we're going to do is we're going to factor out this gamma from the sum from RT plus 2 forward. So what I'm going to do now is I'm going to take gamma as a common factor for RT plus 2, gamma squared RT plus 3, gamma cubed RT plus 4, and so on. And then what I can write is gamma into, right, multiplied by RT plus 2, gamma RT plus 3. Then you will have gamma squared RT plus 4, and so on. Conditioned, of course, on ST is equal to S. So this part here did not change, right? So we wrote that the value of the state, right, we just used this equation. We factored out gamma in order to arrive at this equation. But now this is interesting, because if we look at RT plus 2 plus gamma RT plus 3 plus gamma squared RT plus 4, well, this is the same as this GT, but a index further, right? So if you had done here GT plus 1, if we substitute T by T plus 1 in this equation, we will get RT plus 2 plus gamma RT plus 3 plus gamma squared RT plus 4, which is nothing but what you see in this purple box, right? So this is like the sum of rewards after T plus 1, right? So from that state, T plus 1 onwards. So therefore, instead of this summation, I'm going to just write GT plus 1 here. So I'm going to have expectation of RT plus 1, which didn't change and didn't change from here, plus gamma. And instead of this, I just use the definition of the random variable. And then that would be GT plus 1. Of course, all conditioned on ST equals S. Now, I think this should appear to you that we're actually doing something useful here, because as I told you, we would like to arrive to this equation, right? So therefore, I want to see GT plus 1 on the right-hand side of my equation. And we already see that, which is great. Now, of course, the conditional expectation is not yet fully correct to write the value function, but we're going to get to that in a second. So the next step, all I'm going to do is I'm going to just use the linearity of the expectation, which means that expectation of A plus B is expectation of A plus expectation of B. And please notice that gamma is a constant, and expectation of a constant multiplied by the random variable is nothing but the constant multiplied by the expectation itself. That's why I can take gamma outside of this expectation and have this addition here, which is ERT plus 1 conditioned on ST equals S plus gamma EGT plus 1 conditioned on ST equals S. So this is great. We see GT plus 1. But what is missing to actually replace this expectation by V of ST plus 1, right, is the conditioning on ST plus 1 equals to something which I'm calling S prime. So how are we going to introduce that? So you couldn't simply, just come here and say, oh, this is the value of the state ST plus 1, because it's not, right? Because the value of the state ST plus 1 needs to be conditioned on ST plus 1. And this here is conditioned on ST equals S. So the way we're going to do that is using the rule of the iterated expectations, which we proved in a previous slide. And that rule could simply be stated as follows. So the conditional expectation of y given x equals to some value could be written as a nested expectation or an iterated expectation, whereby we can introduce a new random variable z and set it to a certain value. So we proved that before, that E of y given x is E of y given x and z conditioned on x, right? So now all we're going to do is we're going to just use this law inside this equation. So the way we're going to use it is we're going to call the random variable y in this equation to be gt plus 1. We're going to call x to be just st equals s, right? So x equals x corresponds to big st equals s, which is this chunk here. And now we're going to introduce what we are missing, right? Because we said we're missing st plus 1 for us to be able to write this v phi of st plus 1. So what we're going to do now is we're going to introduce z to be equal to c to be st plus 1 is equal to s prime. Now, once we introduce that and apply this equation to expectation of gt plus 1 given st is equal to s, we will get the following equation. So the first part remains the same. It remained the same here. 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 And now the second part, what's going to happen is we're going to just apply this equation whereby we will have e of y, but y is gt plus 1, so it gets this term, conditioned on z equals z, which is st plus 1 equals s prime, and that's this term. And now you might wonder, where is x equals x, right? Where is st equals s? Well, I definitely would need to put st is equal to s, but we have to notice that gt plus 1 only depends on st plus 1, really, right? So that's why conditioned on st plus 1 is enough for me to get gt plus 1. And that's why I could actually, I didn't write x equals x, because I know it does not, this is sufficient, right, for me to determine gt plus 1. And of course, the chunk st is equal to s has to remain. We cannot get rid of that. But now this is interesting, because after we use the law of iterated expectations, we arrive to this place where now you have the expectation of gt plus 1 given st plus 1 equal s prime, right? Well, if we look back, the value of st plus 1 is nothing but the expectation of gt plus 1 given st plus 1 is equal to something which we call s prime. So now we could simply replace v pi inside here, and that v pi will be v pi of st plus 1 is equal to s prime. So all I have done from this step to this step is use the definition of the value function, which was the expectation of this random variable, which is like the reward to go. And then I will have now expectation of rt plus 1 conditioned on st equals s plus gamma expectation, this outer expectation, of course, of v pi of st plus 1 is equal to s prime given st is equal to s, right? So from here to here, just use this definition. Now, by the linearity of expectation, so the same thing we applied here, we will apply it again, right? But now to collect the variables, not to, like split them as we did before. So now we have e of a plus gamma e of b, and now I can write that as e of a plus gamma b in under one expectation. So now you see that this is already very close to what we would like to achieve, because we have arrived to a place where we have the value function at state st is equal to s to be a function of a recursive function of st plus 1 equals s prime. Now, the only thing that is remaining to happen is we need to expand this expectation in terms of the definition of the expectation, which is the summation of the probability of certain event to happen multiplied by the random variable. And in our case, the random variable is this whole chunk here, right? So that's rt plus 1 plus gamma b st plus 1 equals s prime. Now, this expectation, as we said, is over the action and over the MDP, which means now we can write it as the summation over the probability of taking an action, which is given by pi or the policy, and then the probability of being in a successor state condition on a state and an action. And we, of course, sum that over all possible successor states. Inside here, the v pi stays the same, as you see, right? V pi st plus 1 is equal to s prime. But now rt plus 1, right? What is rt plus 1? So it's the reward I will get at time step t plus 1. So given I was at this state, applied an action, observed st plus 1, which we know is equal to s prime, right? I will get the reward. And that's why we will get the reward of sa s prime. Now, if it's confusing how I expanded this expectation, do let me know in the comments below, because I can explain that again from the way we derived the density of the trajectory in reinforcement learning, that the only difference here is we don't have a full trajectory, we just took a triplet. So here we took a triplet of the action state and successor state, and we were able to factorize it using just the chain rule in this way. So yeah, I hope this helps. I tried to keep it under 15 minutes, and I think I'm doing okay on that. I'll see you next time with another set of slides. Thanks a lot.